Hi. So I can't see anybody apart from people in the first row of tables. So if I say anything funny, you have to laugh really loud so I know you're there. Okay. Brilliant to be back at Golang UK. Did anybody come and see me speak here last year where I talked about containers? I can see a few hands, a few people. Right, so in that talk, I was talking about how a container is put together, and I will have talked about creating namespaces using Syscalls. And I did that talk a few times, and I thought I should really understand what I mean by these Syscall things. I want to, dive into that. I want to understand it better. So what I'm going to be talking about this afternoon is, well, what are these Syscalls? How do they work? What can we do with them? What kind of fun things can we do with them? I work for a company called Aqua who do security for containers, so I'm pretty interested in security as well, and I'll touch on what Syscalls can do to help us with that as well. Right, so when I wanted to find out what Syscalls were, kind of the obvious first place to look is Wikipedia. And Wikipedia gives a pretty good definition. It tells us system calls are the way that your user space program requests services from the kernel of the operating system. Why does it need to do that? Well, because it turns out your user space program really doesn't have very much in the way of privilege. There are loads of things that your application can't do by itself. It has to ask for assistance from the kernel. That includes things like writing to a file, opening devices, writing to the screen, any kind of communication, creating new processes, even finding out what the time is. You need the kernel to help you do that. Anybody ever done any of those things in your programs? Yes, right, okay, so you've all used Syscalls, yeah? And you can see which Syscalls you're using a utility called strace. So let's have a quick look at strace. Is this big enough? Anybody at the back who can't see? I'm going to assume it is big enough, but shout if it's not. Very, very simple hello world program here, or hello Golang UK rather. And we can just build that, and we can use strace on it, and we can see a lot of system calls happen. There's a lot of system calls here. Right, so it's like 4:15 on a Friday afternoon, and I don't really think we want to walk through all of these individually. That would be really dull, right? So the interesting ones, right up here at the top, we've got exec_ve. So that's the system call that says run this program, and we can see it ran hello. Seems pretty good. Some stuff happens, and we cut to the chase. We get all the way down to the end, where we can see the, I don't know if you can see it down here, but the right system call here that does the work. It wrote out the 16 characters of Hello Golang UK and a lot of other intermediate stuff. But that's the one we're interested in, right? The right call is what did what we really wanted it to do. So how did we get from the format println function to calling that syscall? So we can use code to help us find that. So println calls fprintln. Fprintln passes stood out. Fprintln, the work is done here. We've got this write function that's been called on stood out. Stood out is not terribly surprisingly a file created by new file. We can look at file. And inside here, if we search for the write function, we can see that it calls syscall, a write function in the syscall package. So a few layers down from the code that you're all familiar with, we'll find the syscall package. Let's have a look at what the syscall packaging Go looks like. So the documentation tells us that the Syscall package is an interface to the operating system primitives. That agrees with what Wikipedia said. This is good. And it tells us that it varies according to the operating system and the architecture that we're running on. It tells us that it would prefer us to go and use other higher level packages rather than this one, but that doesn't sound like fun, so I'm going to use this one. And it also tells us at the end here, for further details, you're going to have to consult the manuals for the appropriate operating system. So pretty much from here on in, we have to look at the Linux man pages. I'm using Linux as my operating system. I believe there are other operating systems that exist. The principle is pretty much the same, but for the purposes of today, we'll talk about Linux. Okay, so inside the Syscall package, we've got some operating system specific files, and we've got a bunch of auto-generated files that give us all these different combinations of operating system and chipset architecture. So on my Mac, it's an 86 processor. And if we look at the implementation of write inside the Syscall package, we basically see the work is done here by a single function called Syscall. We pass in this syswrite, it's the identifier for the system call that we want the kernel to execute for us. And basically all syscalls are kind of the same. They have a first parameter that tells us which syscall we want to have the kernel do for us, and then some number of parameters that we're going to pass. So there are about 300, I think it's 303 system calls in Linux, and some of them are really esoteric and, do some crazy things, and some of them you use all the time, like these first four, like reading, writing, opening, closing. That, we can understand what those are doing. So, system calls, what happens when you call that syscall function? So we go and look at the man page, and it tells us that syscall saves some CPU registers before making the system call, and it restores the registers when the system call returns. And it tells us a bit about error handling, but there's a big gap there between the before the system call and the returning from the system call. So I'm not really satisfied with that explanation. Go and find out what is actually happening in the meantime. So the user space code, that syscall function, sets up a register with that syscall ID. On my x86 processor here, it's using this register called AX, and that identifier tells the kernel what system call code we want it to execute for us. And then we have this table that, I'll get the pointer up, gives us like which parameters we want to pass in, or where to write those parameters into which register. So for our friend, the write function, or the write system call rather, we're going to populate some registers with like the file we want to write to, and the address of the data that we want to write, and the length of the data. So we set up those parameters into the place where the kernel is going to expect them. And then user space does this trap. It's like an interrupt, telling the kernel that it wants it to take over. And the kernel can then run its code. It knows which code to run based on what this identifier in the AX register is. And it can pull the parameters from the other registers. It does whatever it needs to do, like writing to the file. And when it's finished, it writes the return code into that AX register again. And then it hands control back to user space code. If we had a different CPU, there might be a different set of registers, but it all basically works the same way. There's like a table for which parameter goes into which register. So system calls are really giving us this interface between Linux, the operating system, and your chipset. And there's only that one function, right? The syscall function. So we don't need to have an implementation of all of those system calls, not all 303 of them. You could just implement the ones that you are interested in. Same kind of thing applies if you want to emulate Linux on some other operating system. This is exactly what Microsoft did when they implemented the Bash shell on Windows. They wrote an implementation of some subset of the Linux Syscall interface enough that you could run a lot of common bash operations. Now, I don't know if this is exactly true, but I heard that they did about 200 of those 300-odd different Syscalls, and that was all they needed to really create a usable bash shell on Windows. OK, so if you only had to implement a subset of the system calls, maybe you want to write your own emulation for some other crazy piece of hardware or software or operating system of your own, how would you know which syscalls you needed to implement? Well, you only need to implement the ones that are being called. And we can use a -c flag on that strace utility to see which ones are being called, or to get a count of them all. So I go back to my strace of hello, and I just put -c. And there was basically a dozen system calls used to run that little hello world, or hello Golang rather, utility. But that would be all we'd need to implement. So how does strace get this information? How does it know what different syscalls are being called? And the answer is another syscall. It's called ptrace. And the ptrace system call is pretty special and pretty powerful. Ptrace allows one process to observe and control the execution of another process. It can examine and change memory and registers from that other process. So imagine you can grab hold of another process and change it while it's running, which is a really kind of scary thing, that somebody could grab hold of your running process and change it while it's operating. But then you think about it, that's something that you actually do when you're running a debugger. Ptrace could be used by hackers to do terrible things, and it could also be used by the rest of us to do sort of normal things like debugging and system call tracing. Ptrace is pretty special. It's, well, we call it with the normal syscall interface. If you're really observant, you'll see it says Syscall 6, and I said that there was only one syscall function. Well, there's actually two. It's just because the original one only takes, I think it's 4 parameters, and then there started to be some syscalls that needed more than 4 parameters, so they have another one called Syscall 6 that allows you to pass in 6 parameters. So in the case of ptrace, we're going to pass in the ptrace code, the syscall code for ptrace. And then we also pass in this parameter called request, which identifies a subcommand from ptrace. And there's a whole bunch of things that you can do inside ptrace by calling these different subcommands. The Go syscall package actually wraps a whole load of those up into some nice convenient functions, which are convenient partly because they're easier to call, and they're also convenient because it gives us an idea of what sort of thing you can do with ptrace. So you can attach to a particular process, you can read the registers from the process, you can look at data inside that process, you can change it, you can set registers inside that process. You can also step through that running process. This really does sound like what you do in a debugger, right? So armed with the fact that we can do all these things with ptrace, I think we should write our own version of strace. OK, so I have a little tiny starting point here. At the moment, this function, all it does is, well, it lets us run an arbitrary command. So we're going to call it, we're going to pass in the name of a program we want to run. Maybe there are some arguments to that program. We set up this command structure. We wire up std in, std out, and std. And then we start that command, which is basically start a new process, run this program, whatever it is. And we're going to wait for that to return so we can see whether anything strange goes on. And so at the moment, we're not doing anything terribly exciting, but just to kind of prove what we're doing. I'll build that. And let's do my strace on that hello program that I just wrote. It says it's going to run the hello program, and it prints out hello Golang UK. That's not terribly impressive, right? Okay, so let's turn on p-tracing. And we do that by passing in a sysproc attribute. Sysproc attribute. And we're just going to say, please turn on ptrace. Okay. So we'll build that and run it. And we see that it returned this trace breakpoint trap. And then it also printed hello Golang UK, just like it did before. To show what's really happening there, we'll just put a little delay in at the end. So we'll just sleep for 3 seconds, I think we'll do. And we'll build it. Oh. Second, thank you. This is good. My code reviewers are awake, even though it's Friday afternoon. Hey. Right. So we see it immediately calls that trace, or tells us about this trace breakpoint trap stop. And then it paused for the 3 seconds before it wrote out hello Golang UK. What's happening is we start that child process. It immediately, because we've turned on ptrace, goes into this breakpoint state. So we get this error message. The parent process sleeps for 3 seconds, and all the time it's basically holding its child process in its debug state, just like if you'd put a breakpoint in your debugger. And then when the parent process, when this timer expires, the parent process finishes, and then there's nothing to hold up the child process anymore, so it just goes on, doing what it would have done, prints out hello Golang UK. And so that's kind of just to explain why those things happen in the order they happen. So rather than sleeping here, what I'd like to do is print out the state of the registers. And I can use ptrace to do that. So ptrace get registers. And I'm going to get them from a particular process ID from the child. And I'm going to write them into a register structure. The process ID, let me just bring this up the screen a little bit. The process ID comes from that command we just set up. So this is the child process ID. And we want a structure for these registers. ptrace registers. We'll panic if this goes wrong. And we want to print out what this structure contains. Oh, right, %. Why does it need so many key combinations to print out one structure? Right. So this is called regs. Okay. Okay, so we get this structure full of registers at the point where this breakpoint has happened. If you were paying really close attention, you might remember that on this machine with its 86 processor, it's the AX register we care about. Now, the AX register, if I can find my pointer, currently has 0 in it. There's also another interesting field in here called orig, RAX. It's the original state of the AX register. So you remember when we return from a system call, we get the return code written back into the AX register. So what's actually happened is this is returned. RAX contains the return code, which was 0 because everything went well. And the system call that we called at the time is in this original RAX field in the structure. So let's find out what that field is. I have a little convenience bit of code. The code is on GitHub, so you can look at it at your leisure, but just initialize this, and then I have a get name function in here, which will map the can't spell the original AX register, and that's going to be a string. So let's print out. So this is going to tell us the name of the syscall at this point where we've gone into the breakpoint state. So, and then we see exec VE. And do you remember that was the first thing we saw, the first syscall we saw when we ran this under strace? So that's pretty encouraging. That's the first syscall we expected to see. So now what I'd like to do is have the program run on to the next system call so I can trace that out. And there is, conveniently enough, a ptrace subcommand called ptrace syscall, which does exactly that. It arranges for the tracee process to stop the next time we hit a system call. And this is going to look like a sig trap to the parent process, the tracing process. So let's call that function. Really want to bring this up the screen again. So syscall ptrace syscall on that process ID. If anything goes horribly wrong, we will collapse in a big heap again. And we need to wait for that sig trap to happen, and there's a convenient wait for function we can call. Nil, 0, nil. Again, let's panic if that goes wrong. So at this point, we should have, well, the child process has run on to the next syscall, and the parent process has waited for that to happen. So now I'd like to print out the state of the registers again at this point, but rather than copy the code from up here, I'm just going to put it into a nice big loop. So we'll loop around all of that. So we should repeatedly run to the next system call, trace out the state of the register, or trace out the name of the syscall rather, not the whole registers, and run on to the next one, and so on and so forth. So, oh, I know. Try that. Okay, so good news and bad news. The good news, we have got lots of system calls being traced out. This, kind of moving in the right direction. And the bad news is obviously this panic. So we can see here, it's panicked because there's no such process, and it's happening on line 36. So line 36 up here, we've tried to read the registers from a process that doesn't exist. And the best explanation for that is that that process has exited. So I'm just going to say, well, when that happens, we'll just quit out of this loop. So let's try that. The good news, we have got rid of the panic. But there is something pretty suspicious going on here. Everything seems to be in pairs. Even more suspiciously, if we look at the write function down here, there's two, it says write twice, either side of that text that we wanted to be written out. And the clue to what's going on is right here in the man page. So it does say, arrange for the tracee to be stopped at the next entry to or exit from the system call. Okay. We read in the man page a bit further. Tracee enters a stop state just prior to entering a system call, and it enters another stop state when the system call is finished. Those two stop states are indistinguishable from one another, and it's our responsibility to keep track of the sequence. This comes straight out of the man page. I didn't make this up. This is really what happens. We have to do this. Okay. So I think we can take a pretty good guess that if we go right to the beginning, we only see one instance of exec_ve rather than a pair, which suggests that it had completed. We were on the way out of the system call when we saw this breakpoint, and that totally makes sense because we've just started running a new program. So we start in this kind of exit state. So I'm going to say that it's exit. Every time through this loop, we're going to sort of flip the state of exit. Ooh. Not what I meant at all. That's what I meant. We're going to flip the state of exit, and we will only print out the system call if we've just completed it. Okay. So that's starting to look quite convincing now. We can see a whole load of system calls that starts, if we go up to the top, it starts with exec_ve, it ends with write, just after we've seen that text being printed out to the screen. We could even go so far as to trace out the return code. I'm going to say we'll do it in decimal. So we want the RAX register. And we can see if we look at the return code from write, it's 16, and that's exactly what we saw when we used strace, that it's written 16 characters in hello, Golang, UK, new line. So we've basically written strace here. The last thing I want to do is I want to sum up the number of times we called each of those different system calls. And I can do this again with a little convenient bit of code that just increments a counter for each different system call that we make. And we can print them out at the end. Okay, so we can see the total number of times we called each of those system calls. And if we compare that to strace of the same program, it looks pretty convincingly the same. 1 call to write, 7 to mmap, 1 to munmap, 114 to RT-sig action, and so on and so forth. So we have written an implementation of strace from scratch. I think that's pretty cool, right? Okay, so I also wanted to talk a little bit about how system calls relate to security. Anybody heard of a thing called seccomp? Not too many hands. Okay, right. So there are things called Linux security modules, one of which is seccomp. And this all relates to the principle of least privilege. So least privilege is really about saying you give people or entities or bits of code the least privileges that they need to do their job, and then that keeps things more secure. It's exactly the same thing as, you don't give everybody who passes your house a key to your house. You only give keys to your house to people who need to get into it. So least privilege, only give permissions, only give the ability to do things to the entities, the code that need it. And particularly as we talk about microservices, this makes a lot of sense. You can really easily think about what a microservice should be able to do. Suppose you've got a microservice that, let's say it's going to read things from a product database. And it never needs to write anything. And it certainly never needs to communicate with some other process. It certainly doesn't need to be able to ptrace anything else. So the idea of seccomp is to say, we're going to set up a security profile that says which system calls a process is allowed to execute. You can then pass these seccomp profiles to containers, as an example. So Docker lets you pass in a seccomp profile in JSON format, for example, and that attaches the profile to this container, and it says that container can only run the system calls or execute the system calls that are defined in that seccomp profile. I'm just going to have a little moment to mention a project that I'm working on called Manifesto, which is really new and kind of prototype stage, but with love feedback and stars. One of the ideas of Manifesto is that you could store, well, the point of it is to store container metadata alongside your containers in the image registry. And seccomp profiles are a really good example of the kind of metadata you might store. It is written in Go, so lovely. So seccomp profiles are JSON files. This is the beginnings of one. Well, the whole file is there. I've only copied the first few lines of one that Jess Frizzell wrote and put on the internet. And there's a really good blog post she wrote about how she generated this seccomp profile. And might be a little bit small, but you can basically see it says, oh, here's the name of a syscall, and yeah, we're going to allow that one. So it says, are you allowed or not allowed to execute that particular system call? So let's try building one ourselves. Now, I wasn't really confident that I could type this all out quickly enough, so I have a little bit of pre-prepared code here. So we're going to disallow one system call by name. We pass in the name and convert it to its identifier, so that's sys_code that identifies that particular syscall. We're going to create a seccomp filter, and by default, we allow everything. And then we add a rule where we say that particular syscall we want to disallow, we're going to return an error code. And the particular error code we're going to use is eperm, which is operation not permitted. And then we have to load that filter to actually make it work. So if I go back to my strace code here, I can call that function. And let's say we disallow write, our friend write. Okay. So we'll build that. And let's run that on echoing hello. And it printed out that it was going to run echo hello, and then it didn't do anything else. And the reason why it didn't do anything else is because I prevented it from writing anything else out to the screen. It might have been trying, but it couldn't tell us because I stopped it from writing anything to the screen. So, yeah, maybe, Liz, that is not the most convincing demonstration. Perhaps we need to choose a different system call that we're going to disallow. So let's just really quickly see what gets called when we echo hello. And the next candidate I'm going to pick is open. So rather than disallowing write, I'm going to disallow open. In a real world scenario, you wouldn't be writing code like this. You would be building a profile, but it's really just to illustrate what's happening under the covers. So we'll build this. And okay, so we can see that some system calls got called, but eventually we tried to do open and we got operation not permitted. And it was open. The open was called because it was trying to open some kind of shared library file because it echoes written in C. So we've basically seen how seccomp can prevent your code from calling a particular syscall, should you so choose. So that is really the demonstration of syscalls, the demonstration of seccomp. Just to sum up, system calls are your interface into the kernel, and hands up anybody who prior to this talk had ever actually deliberately imported the Syscall library. A few hands, right. So now all the rest of you know that you are calling Syscalls all the time. Your code is mapping down to those Syscalls all the time. Those Syscalls give you the interface to the operating system. It's how Linux, and any operating system, it's how it works. And it's an interesting portability layer, an interesting emulation layer. We've seen how you can watch what system calls are going on using strace. We've seen a little tiny bit of what you can do with ptrace. And I think the next thing would be to look at manipulating your running program using ptrace. And we've seen how you could use seccomp profiles to limit which syscalls your program is allowed to actually call. If you want to see the code, it is available on GitHub, strace from scratch. I think we've probably got a few minutes for some questions, if there are any. Otherwise, just go into rapturous applause, because I can't see you and whether or not you all look confused. Anybody got any questions? Yeah.
Hello. Those actions in the list.
Shall I go back and look for that action?
Please, yeah. It was in the terminal.
Oh, in the terminal.
When you.
What was I doing at the time?
It was when you had all the listing.
Okay, so something like
There's loads of those like sys.
all these SIG action ones?
Yeah.
Right. That's a really good question. So I'm not sure the mic was working. So the question is, what is all this RT SIG action stuff? This happens in every single Go program. This is actually a kind of really interesting question. It also relates to, why you end up with additional threads when you start a Go program. These are to do with mapping what happens when you get different signals. And there's one for, I've not actually checked, but I'm going to assume this is all of the possible different signals that you could have. And I'm pretty sure this is to do with concurrency handling in Go, so you wouldn't see this in a C program, for example. Yeah. The other interesting or sort of related thing is, if I can find my mouse, you see there's like a clone call here and another one here. And I'm pretty sure that clone is creating a new process. And one of those is the garbage collector, and the other, I think, is something to do with concurrency and the signal handling. So, really interesting question. Any other questions? No, everybody's mind is blown. Or they've fallen asleep because it's Friday afternoon, and I totally understand that. All right. I think that's it. Thank you.
Awesome.